Welcome to the Deep Dive, where we plunge into the heart of groundbreaking research, cutting through the noise to bring you the most fascinating insights and surprising facts.
Glad to be diving in.
Today, we're diving headfirst into a world where an invisible threat lurks within the very silicon of our digital devices, something called side-channel attacks. These aren't your typical digital intrusions. They're far more subtle, quietly exploiting the physical way our hardware operates.
Exactly. The physical side of things.
Our mission today is to give you a shortcut to being truly well-informed about how we can protect the absolute foundations of our digital security, those incredibly complex cryptographic algorithms.
The bedrock, really.
Especially when they're implemented on specialized hardware known as FPGAs, or field programmable gate arrays. We're going to unpack the ingenious findings from a groundbreaking academic paper titled Optimal Placement of TDC Sensor for Enhanced Power Side Channel Assessment on FPGAs by Das et al.
A really significant piece of work.
And this research isn't just about bolstering security. It's about pioneering a highly efficient, Probeless method to assess hardware vulnerabilities before devices even roll off the manufacturing line.
That before is key.
Imagine the seismic shift this promises. Massive reductions in cost, dramatically shorter development times, and, well, a future where proactive security is simply built in. This isn't just security, it's the epitome of smart, forward-thinking design.
It really is about smart design from the outset.
Okay, let's unpack this then. We talk about cryptographic algorithms all the time. They are, quite literally, the mathematical fortresses protecting our most sensitive data.
Right. Designed to be computationally impenetrable. A mathematical lock so complex you couldn't brute force it.
We trust them with everything. Our bank accounts, personal communications, national secrets, critical infrastructure.
Everything.
But here's the twist, and it's a profound one. The math itself might be perfectly secure, an uncrackable cipher, but the physical way that math is implemented on a tiny silicon chip, well, it can inadvertently betray those very secrets.
That's the crux of it.
It's like building an impenetrable vault door. But the mechanism for opening it makes a distinct series of clicks and whirs that someone nearby could learn to interpret, revealing the combination without ever touching the lock itself.
That's a great analogy.
Yeah.
And what's truly fascinating here is precisely that distinction you highlight. We're talking about side channel attacks, or SCAs.
Right.
As you said, these aren't about trying to crack the encryption algorithm directly by, say, guessing keys or finding some mathematical weakness in the code itself.
No brute force?
No. Instead, SCAs are about observing the physical manifestations of the computation as it happens on the hardware.
Okay, physical manifestations, like what?
Well, continuing your excellent analogy, imagine listening to a professional safecracker. You're not trying to pick the lock directly, but you're inferring the combination by paying incredibly close attention to the subtle sounds, the tumblers falling into place maybe, or maybe the minuscule vibrations traveling through the floor, or even slight changes in the electromagnetic field around the safe as they manipulate the dial. These are the side channels, the unintended physical leaks that occur during a supposedly secure operation.
Gotcha. So physical clues leaking out.
Exactly. In the nuanced world of hardware, this translates to attackers monitoring things like tiny transient fluctuations in the chip's power consumption as it performs a cryptographic operation.
Tiny power spikes or dips.
Precisely. Or perhaps they're detecting faint electromagnetic radiation emitted by the chip.
Like radio waves?
Sort of, yeah. Very faint, very localized. Or meticulously measuring precise timing differences in how long certain operations take.
So some calculations take fractionally longer than others, and that tells you something.
It can, yes. Or even observing how the processor's internal memory cache is accessed and used. All these physical side channels inadvertently leak information about the secret operations being performed inside that mathematically secure cryptographic core.
They're like whispers carrying secrets from a supposedly soundproof room.
That's a perfect way to put it. And the danger here is profound, because these leaks can allow an attacker to extract secret keys, even from cryptographic algorithms that are mathematically proven to be unbreakable in theory.
Wow, so it just bypasses the math.
It bypasses the mathematical strength by exploiting a physical weakness. And this isn't some theoretical boogeyman confined to academic labs. It's a very real and present danger that has been demonstrated repeatedly.
Right, the paper mentions some examples.
Yes, the source material references several concrete, unsettling examples. We've seen these attacks successfully demonstrated on a wide variety of embedded devices Think smart cards for banking.
Okay.
High-performance computing platforms, even on the x86 processors found in many of our everyday computers. The paper cites instances like attacks on Zigbee devices in the IoT space.
Like smart home stuff.
Potentially, yeah.
Yeah.
Or side-channel issues found in Apple's Titan security chip. Even software-based power side-channel attacks on standard PC processors have shown how pervasive this threat truly is.
So it's everywhere, basically.
It's a widespread concern, yes. These aren't just lab curiosities. These are real-world threats that impact the security of devices we rely on every single day, from smart homes to secure government systems.
Okay, that really drives home the point.
And this brings us to a critical need that drives this entire area of research: the pre-manufacturing assessment of these devices.
Assessing them before they're made.
Exactly. Before a chip goes into mass production, perhaps destined for millions of smartphones or IoT devices, or even critical things like medical implants. Assessing its resilience to SCAs is absolutely crucial.
Why? I mean, it sounds obvious, but spell it out.
Well, because discovering these vulnerabilities after millions of chips have been fabricated, packaged, and deployed is just incredibly expensive.
Right. Recalls, patches.
Exactly.
Yeah.
Think about the economic impact. Costly recalls, complex over-the-air patches that might not even reach all the affected devices.
And the reputation hit.
Huge reputational damage. And perhaps most importantly, significant delays in getting a product to market. Time to market is everything in this industry.
So it's an economic and security nightmare if you find it late.
Precisely. It's not just an economic imperative, it's a fundamental security requirement to catch these issues early, right at the design phase. This is exactly where that smart design truly comes into play, building security from the ground up, not trying to patch it on later.
That makes perfect sense. Dealing with recalls and patches after millions of devices are out in the wild sounds like an absolute nightmare for any manufacturer.
Okay, so traditionally, assessing this kind of subtle power leakage involved physical probes, right? Like literally sticking tiny sensors onto the chip.
That's right. Tiny needles or contact points placed directly on the silicon die or the package.
Which sounds different. Oh, it is. It's invasive, it's expensive, incredibly complex to set up accurately, and not exactly practical when you're dealing with early-stage designs or trying to test during the design phase itself. It's a bit like needing to surgically attach a monitor just to get a blood pressure reading, not ideal for routine checks.
Yeah, not scalable. But this paper talks about something revolutionary. Probeless, or remote power SCA. How does that even work, particularly when we're talking about FPGAs? Are we, like, sensing it through the air or something? What's the trick?
No, not through the air. If we connect this to the bigger picture, the trick isn't about remote sensing in that sense, but rather building the sensors directly into the chip itself, making them part of the device under test.
Ah, okay, so the chip spies on itself.
In a way, yes. And FPGAs, field programmable gate arrays, are absolutely ideal for this kind of assessment. Think of an FPGA as a digital chameleon. It's a highly flexible hardware platform.
Right, you can reprogram them.
Exactly. Its internal digital circuits can be reconfigured or reprogrammed on the fly, even after manufacturing. This incredible flexibility means that instead of relying on external invasive probes, researchers can actually build these voltage sensors directly onto the FPGA fabric, right alongside the cryptographic core they want to test.
So the sensor becomes part of the design you're testing.
Precisely. These on-chip sensors become an integral part of the very hardware being assessed, providing an internal diagnostic capability. And specifically, this paper focuses on using what are called time-to-digital converters, or TDCs.
TDCs, okay, what are those? Time to digital. Sounds like a stopwatch.
That's actually not a bad way to think about it, a very, very precise stopwatch. Let's break down what a TDC is and how it ingeniously functions as a voltage sensor. Imagine a TDC not as a thermometer for voltage, but as a finely tuned electronic racetrack.
Okay, a racetrack.
When an electrical pulse is sent down this track, it passes through a series of tiny gates. The paper calls them cascaded delay buffer elements.
Hurdles on the track.
Sort of, yeah. Each of these gates introduces a very slight but consistent delay to the pulse. So the pulse starts at one end and races towards the other, accumulating tiny delays at each gate.
Getting slower as it goes.
Well, taking longer. And along this racetrack, at various points, are what we can think of as high-speed checkpoints or cameras.
Got it.
These are implemented using something called D flip-flops, or DFFs, which are fundamental memory elements in digital circuits. These DFFs tap a subset of the outputs from the delay elements.
So they only look at certain points on the track.
Right. They essentially take a snapshot at specific moments to see how far the electrical pulses travel down the track within that window. This specific subset of tapped outputs forms what they call an observation window, defining the segment of the racetrack being actively monitored.
Okay, observation window. Makes sense.
Now, the core principle here is beautifully elegant and rooted in basic electronics. These TDCs measure the signal propagation delay, that's the time it takes for the electrical pulse to travel through those logic elements. Let's call this propagation delay TP.
Okay, TP.
The critical relationship is that TP is inversely proportional to the supply voltage, VDD.
Inversely proportional. So if a voltage goes down, time goes up.
Exactly. In simpler terms, if the supply voltage VDD drops, even by a tiny amount, the electrical signal takes longer to propagate through that delay chain. Think of it like a car driving on an open highway versus hitting a patch of rough road.
Right, slows you down.
On the rough road, the car slows down, taking longer to cover the same distance. The voltage fluctuations are those rough patches that directly influence the speed of the electrical signals. So TP is proportional to 1 VDD. A lower voltage means a longer time TP.
Okay, I think I get that. Voltage drops, signal takes longer. So how does that detect leakage?
Right, so how does this translate to detecting sensitive information leakage? When a cryptographic core, which is our device under test, or DUT,
The thing we're testing.
yes,
Yeah.
when it performs an operation, like an encryption, it demands electrical power. This current draw isn't perfectly smooth. It causes tiny transient fluctuations, we call these droops, in the local supply voltage.
Little dips in power.
Little dips. Now, if a TDC sensor is cleverly placed nearby, sharing the same power delivery network, that's the internal power highway system of the chip we'll talk more about,
Right.
it will literally feel these minuscule voltage changes. These voltage changes manifest as variations in the signal propagation delay TP within the TDC's delay chain. A voltage droop means a longer delay TP.
Because TP is proportional to 1 VD.
Exactly. The TDC then precisely measures these delay variations and converts them into digital bits numbers, which can then be analyzed by researchers. It's essentially converting an analog voltage fluctuation into an incredibly precise digital measurement of time.
Wow. So it's translating tiny voltage wiggles into numbers an attacker might read.
That's the core idea for assessment, yes.
Okay.
It allows designers to see those wiggles clearly. Now, it's worth briefly noting that while TDCs are the star of this paper for Probeless SCA, ring oscillators, or arroways, can also be used. Ring oscillators, they're another type of on-chip sensor. However, TDCs are generally preferred for this specific application because they require significantly less on-chip area for comparable sensitivity.
Ah, smaller footprint. Same result.
Basically, yes. You get more bang for your buck, or rather more precise sensing capability for less valuable silicon real estate, which is always a crucial consideration in chip design.
Right, area is expensive.
Always. Now, this brings us to the initial and really fundamental problem statement that this groundbreaking research set out to solve. Prior work in this area of Probeless SCA often required, well, spreading multiple TDC sensors throughout the FPGA fabric.
Scattering them everywhere.
Pretty much.
Yeah.
While this approach could be effective in theory, it consumes a large area of the chip. Imagine trying to monitor a vast metropolitan area for subtle seismic activity by blanketing it with hundreds of individual sensors.
Yeah, expensive and maybe overkill.
It works, but it's incredibly resource intensive. If you're trying to analyze a really large and complex intellectual property block, say a cutting-edge processor core or a massive AI accelerator,
City designs.
or if you're working on resource-constrained FPGAs where every square micron of silicon area counts, scattering sensors everywhere simply isn't a feasible solution.
You just don't have the space.
Exactly. This is the core challenge.
Yeah.
How do you get the best possible SCA assessment with the fewest, smallest, and most strategically placed sensors? That's the problem this paper ingeniously tackles.
That problem of area consumption makes total sense. Every bit of silicon costs money and adds complexity. But here's where it gets really interesting and frankly a bit counterintuitive to my gut feeling anyway. When you're thinking about placing a sensor to detect those tiny voltage fluctuations from a cryptographic core, your natural instinct might be to put it right next to it, right? As close as humanly possible.
The intuitive approach, yeah.
Yeah. The closer, the better, right? You'd think that proximity would guarantee you catch the strongest signal, like putting your ear right up to a wall to hear a whisper.
Seems logical.
But this paper reveals a surprising and highly significant truth. That intuitive solution isn't always the most optimal. In fact, it can be dramatically wrong.
Yes. This raises that important question that challenges our fundamental assumptions. What if our instincts in this highly technical and microscopic domain actually lead us astray?
Which happens.
It does. The researchers found through rigorous testing that simply placing a TDC sensor closest to the crypto core is not always the best location to sense the maximum voltage fluctuations. In fact, as you said, it can be dramatically suboptimal.
Meaning you might miss the leakage.
You might severely underestimate it or potentially miss it entirely, causing you to completely misinterpret the security of your chip.
Wow, okay, so how did they show this?
Let's illustrate this with the dramatic empirical evidence the researchers present. They introduce a critical metric called minimum traces to disclosure, or MTD.
MTD, minimum traces to disclosure.
Right. This metric tells us how many cryptographic operations, or traces essentially, individual snapshots of the chip's activity during an encryption an attacker needs to observe to successfully extract the secret key.
So lower MTD is bad for security, good for the attacker.
Exactly. Lower MTD means higher leakage, which in turn signifies an easier attack and a more vulnerable system. It's the attacker's benchmark for success.
Okay, so what did they find with MTD?
And the difference they found was truly astounding, a more than 10-fold difference in attack effort, depending on where the sensor was placed.
10 times.
More than 10 times. On an Intel Stratix 10GX FPGA, a TDC sensor placed at what they identified as a high leakage location could recover an AES-128 key in under 200 traces.
Under 200 encryptions. That sounds fast.
That's incredibly fast for an attacker in this context. And this is the crucial part, if that same TDC sensor was placed at a low leakage location on the very same chip, it required over 10 times more traces, sometimes thousands of traces to achieve the same key recovery.
Wow. Same chip, same sensor, just moved. And it's 10 times harder to attack.
Or easier, depending on where you put it. The implication of this is profound and has massive real-world consequences. This stark difference highlights that optimal sensor placement is extremely critical for a successful pre-silicon SCA leakage assessment.
Yeah, you can't just guess.
You absolutely cannot. Imagine a chip manufacturer testing their device, placing a sensor in an intuitively close spot, maybe a low leakage spot, and finding it takes thousands of traces to crack. They might confidently conclude their chip is secure and ship millions of units.
Right, they'd think they're fine.
But then, an attacker, perhaps armed with knowledge from research like this, places their sensor or maybe uses an existing internal structure in that precisely located sweet spot, the high leakage location on the chip, and cracks the key in under 200 traces.
That's terrifying. The difference between thinking you're secure and being wide open.
Exactly. This insight saves companies from potentially catastrophic recalls, immense financial losses, and severe reputational damage. It forces us to be much more precise, much more rigorous in our assessment.
And you mentioned this applies beyond just crypto SCAs.
Yes, the paper notes its relevance for other critical applications, like detecting fault injection, FI attacks, where external glitches are used to force errors,
Okay.
and also for general load monitoring on the chip. It's fundamentally about finding the sweet spot where the physical leakage signal, whatever its source, is strongest and most easily detectable, not just the spot that happens to be closest.
Okay, that's a huge finding. So if simply being close isn't the answer and our intuition can lead us dramatically astray, what is the secret to finding that elusive sweet spot for sensor placement? The paper dives deep into something called the Power Delivery Network, or PDN.
PDN.
Now, that sounds a bit technical, maybe a bit like the electrical wiring diagram for your computer, but you're telling me it's absolutely fundamental to understanding why placement matters so much and where those optimal spots really are.
It absolutely is fundamental. And what's truly fascinating here is that the PDN is far more than just simple wires bringing power to different parts of the chip. It's an incredibly complex, intricately designed, multi-layered structure integrated within the chip's silicon die and its surrounding package.
Multi-layered, okay.
And this intricate structure significantly influences how and where voltage fluctuations, those little droops we talked about, manifest across the silicon. The researchers adopted what they call a white box approach to understand this role.
White box, meaning they looked inside.
Exactly, meaning they didn't just treat the chip as a black box and try different spots randomly until something worked. They fundamentally analyzed the internal architecture and physics of the power delivery system itself.
Okay, so how do we think about this PDN?
To simplify it, you can think of the PDN as the intricate multi-lane highway system that delivers power to every single logic gate, every transistor, every component across the entire FPGA.
Power highways, I like that.
But unlike a simple highway, this system has different layers, like an overpass and an underpass, for power complex junctions, and crucially, internal boundaries or partitions that affect how quickly and efficiently power, and critically its fluctuations, can travel and dissipate.
So like different neighborhoods with their own power grids.
That's a very good analogy.
Yeah.
Some parts might have more power traffic, some might have bottlenecks where voltage can't be delivered as smoothly, and others might have smoother, more stable flow. And these internal boundaries between the neighborhoods are paramount.
Okay, so how did they map this out? They didn't physically dissect the chip, right?
No, their methodology to understand this was truly brilliant. They didn't just guess. They used a sophisticated circuit-level simulation framework called HSPIC.
Ah, simulation. Okay.
HSPIC is a powerful industry-standard tool for high-precision analog circuit simulation. First, they virtually partition the entire FPGA fabric into many small, distinct sectors. Imagine slicing the chip image into a grid of tiny squares.
Like a virtual map grid.
Exactly. For example, 2mm by 2mm for the Stratix 10 FPGA they used, much like the grid lines you might see in an architectural blueprint. This allowed them to precisely map out the voltage behavior across every single one of these virtual squares across the entire chip.
So they could see the voltage everywhere on the grid.
That was the goal. Next, they emulated crypto cores. They would excite specific sectors, they labeled them source 1 and source 2 in their diagrams, by injecting a precisely engineered current stimulus.
A fake crypto operation.
Right. This stimulus mimicked the exact dynamic power consumption signature of a real cryptographic core performing an encryption operation. By doing this, they could then observe the resulting voltage droop those tiny transient voltage fluctuations across all other sectors of the chip.
Ah, so they create a ripple and see where it's biggest.
Precisely. This essentially gave them a detailed voltage heat map of the entire chip, showing exactly where and how intensely those power ripples propagated from the source.
Cool. And what did the heat map show? Where were the biggest ripples?
Well, the key finding, visually represented by the results of these simulations, was a crucial and somewhat counterintuitive insight: the PDN boundary effect.
Boundary effect.
They discovered that the Intel Stratix 10 FPGA's die is not a single uniform power plane. Instead, it's internally divided into 3 separate distinct power grids. Using your analogy, 3 distinct power neighborhoods.
3 grids on one chip.
Yes. For instance, columns 1 to 2 might be one grid, columns 3, 7 another, and columns 8, 9 a third, as indicated by the partitioning in their diagrams. These internal boundaries between these power grids turned out to be absolutely critical to understanding where the leakage signals become most apparent.
Okay, so the action happens at the borders.
It seems so. Let's look at their simulation results for source 1. When they emulated a crypto core, source 1, across columns 3, 5, with column 4 being the center of that activity.
Right in the middle of the second grid.
Yes. They found that the maximum voltage droop was observed not at the geometric center of the activity, column 4, but rather over at column 3, specifically sector 57.
Not at the center, but off to the side, near the edge of that grid.
Exactly. At the boundary between the first and second power grid. This is a clear indication that the closest spot wasn't the hottest spot for leakage.
Okay, but why? Why the boundary?
The why behind this is truly fascinating, and it comes down to capacitance. Column 3 is located at the edge of a power grid, and at these boundaries, the amount of what's called decoupling capacitance is typically lower.
Decoupling capacitance sounds like a shock absorber.
That's a perfect analogy. Think of decoupling capacitors like tiny local reservoirs or shock absorbers for electricity. Their job is to store a small amount of charge and quickly release it to smooth out sudden voltage fluctuations caused by dynamic current demands from things like the crypto core.
Okay, they smooth things out.
Right. Imagine a small teacup versus a large bathtub. If you pour a sudden burst of water into the teacup, its water level, analogous to voltage, will visibly slosh and drop dramatically. The bathtub, with its much larger capacity, analogous to capacitance, will barely show a ripple.
Got it. More capacitance, less fluctuation.
Exactly. So at the PDN boundaries, where these reservoirs or decoupling capacitors are smaller and the power distribution is inherently less robust, those tiny sudden power demands from the crypto core create much more noticeable voltage splashes or droops.
Ah, so the boundaries are where the smoothing effect is weakest, making the fluctuations bigger.
Precisely. It's like finding the weak spot in a bridge where vibrations are felt most intensely. The fluctuations are amplified there.
And did they see this with the other source too?
Yes, a similar pattern emerged for source 2 in their simulations. When they emulated a crypto core across columns 5, 7, the maximum voltage droop was found at column 7, sector 61, which again was near a power grid boundary, the boundary between the second and third grids. The pattern was consistent.
Wow, okay, so the boundaries are key.
That's the primary takeaway from this detailed analysis, what they call coarse tuning for optimal placement. TDC sensors show increased sensitivity and can capture maximum voltage fluctuations when placed closer to the PDN boundaries. That's the big picture for optimal location.
But is it just the boundary? What about how far the boundary is from the crypto core?
Good question. While PDM boundaries are critical, the paper also notes that you still need to account for the relative distance from the device under test, the crypto core itself. You can't just put it on any boundary miles away.
Right. Needs to be somewhat relevant.
Empirically, their ultimate recommendation for optimal placement is kind of an equal split between these factors. The TDC should ideally be placed roughly at the midpoint between the center of the DUT and its closest PDM boundary.
Midpoint.
Okay.
Not right next to it, not right on the boundary, but somewhere in between.
Exactly. It's a precise balance of both proximity to the source of the fluctuations and strategic positioning relative to the chip's inherent power infrastructure, specifically identifying where those fluctuations are naturally amplified by the PDN architecture.
Okay, that is fascinating. So we've gone from just guessing, put it close, to this much more nuanced strategy. Find the PDN boundaries. Find the center of your device and aim for the midpoint. That's a monumental step, solving the where of the problem.
It provides a systematic methodology, yes.
But you said even a perfectly placed sensor needs to focus correctly to capture the signal at the exact right moment. That's where the concept of an observation window and what they call fine-tuning comes in. It sounds like there's yet another layer of precision required here, almost like adjusting a telescope to see a distant star with perfect clarity after you've pointed it in the right direction.
Your analogy of adjusting a telescope is spot on. Capturing the maximum voltage droop isn't just about placing the sensor in the right spot. It's about sampling that fleeting electrical signal at precisely the right moment in time.
Like catching the peak of a wave.
Exactly, like catching the peak of a fast-moving wave. Miss the peak, sample too early or too late, and you miss the most crucial information about the voltage droop's intensity.
And you underestimate the risk again.
Precisely. So let's refer back to our electronic racetrack analogy for the TDC design. The TDC includes this crucial observation window.
The part of the track the cameras are watching.
Right. It isn't a physical window, but that specific subset of the cascaded delay buffer elements whose outputs are tapped by our DFF high-speed cameras. This window essentially determines what part of the propagating clock signal is actually being observed and converted into a digital measurement. It defines the segment of the racetrack where the cameras are actively filming at any given moment.
Okay, so how do you know which segment to watch?
Well, the challenge lies in the fact that the voltage droop isn't a static event, like a steady dip. It's a dynamic, transient response.
A ripple.
Like a ripple in a pond or a pressure wave from a sudden impact. There's a specific global minima, a peak voltage droop, that appears at a very specific, minuscule moment in time relative to the operation causing it.
A fleeting moment.
Very fleeting. If your observation window samples too early or too late, you'll simply miss that peak, and thus you'll dramatically underestimate the leakage or even completely miss a critical vulnerability. You'd only catch the beginning or end of the ripple, not its true intensity.
Okay, so you need to time the snapshot perfectly. How do they do that? Manually.
That would be incredibly tedious and error-prone. To address this, the researchers developed an ingenious algorithm they call a greedy gradient search heuristic.
Greedy gradient search. It sounds complex.
It's clever. It effectively makes the TDC self-calibrating. Its purpose is to automate the process of finding this ideal observation window for maximum sensitivity. This is the crucial fine-tuning step, ensuring the sensor's cameras are perfectly synchronized with the peak of the voltage ripple.
Self-calibrating. I like the sound of that. How does it work?
Okay, imagine you're tuning an old analog radio. You might start by sweeping broadly across the dial to find roughly where the station is.
Right, you get some static, then maybe some music.
Once you hear a hint of a signal, you then fine-tune it, making tiny adjustments to the dial back and forth until the signal is absolutely crystal clear, no static, perfect reception.
Got it. Find the strong spot, then zero in.
This greedy gradient search works very similarly. It starts by testing a few initial observation windows. Those are the broad sweeps. For each window, it captures one power SCA trace, one snapshot of the leakage.
Okay.
It then identifies the window that produces the highest deviation in delay values. Remember, Bigger delay deviation means bigger voltage droop. That's finding the clearest signal.
Finding the loudest part of the static?
Exactly. Once a promising window is found, it performs a fine-grained gradient search around that area, making minuscule iterative adjustments to the window position, shifting it slightly earlier or later in the delay chain to really zero in on the absolute optimum point of maximum sensitivity. It keeps adjusting until it finds the loudest, clearest leakage signal.
Okay, automated fine-tuning. That's smart. You mentioned something about a DC bias point, too.
Yes, that's a critical aspect they highlight for this fine-tuning, and one that ensures the sensor can capture the full dynamics of the voltage fluctuations. The DC bias point of the TDC output.
DC, like the baseline.
Exactly. It's essentially the baseline output value of the sensor when no crypto operation is happening when the chip is idle. If, for instance, your TDC output ranges digitally from 0 to 63, you'd ideally want the baseline value, the DC bias, to be somewhere around the midpoint, say 20 to 40.
Why the
Think of it like setting the needle of a seismograph right in the middle of its scale before an earthquake. Why? Because it allows the TDC to capture the full swing of voltage fluctuations, both the downward droops when power is drawn and any upward overshoots that might occur during rapid cryptographic operations.
so it can measure dips and spikes from the baseline.
Precisely. If your baseline is too high, close to 63, a big droop might go below 0 conceptually, but the sensor can't measure below 0. Or if it's too low, near 0, an overshoot might go above 63. In either case, the sensor would clip the signal.
It misses part of the fluctuation because it hits the measurement limit.
Exactly, like a seismograph needle hitting the top or bottom of its paper. So centering the baseline ensures you capture the whole picture.
And the algorithm adjusts this baseline.
Yes, the greedy search helps find the window that naturally results in this optimal DC bias point. If the algorithm finds the DC value is too high, meaning the baseline is too close to the upper limit, it intelligently shifts the observation window to later stages in the delay chain to bring the baseline down. If it's too low, it shifts it to earlier stages. It iteratively converges to that optimal midpoint.
So it centers itself automatically.
It does. And the crucial benefit of this whole self-calibrating algorithm is its ability to automatically compensate for any process, voltage, and temperature, PVT variations, that might occur during chip operation.
PVT process, voltage, temperature, right.
Exactly. Chips don't behave absolutely identically across different manufacturing batches. That's process variation.
Like snowflakes, no two are exactly alike.
A good way to put it. They also behave slightly differently at slightly different operating voltages, voltage variation. And of course, their performance changes with temperature variation.
Real-world conditions aren't stable.
Not at all. These PVT variations can subtly shift the sensor's optimal operating point, changing where that ideal observation window should be or what the baseline DFI value is. This clever algorithm ensures consistent accuracy and maximum sensitivity despite these inherent manufacturing and environmental fluctuations. It makes the sensor robust, reliable, and truly adaptive in any operational scenario.
Okay, that's incredibly clever. So we've nailed down the perfect location for our sensor by understanding the intricate power delivery network, and we've achieved the perfect focus by cleverly fine-tuning its observation window for maximum sensitivity, even adapting to PVT changes. That's fantastic for accuracy.
It covers the where and the how well.
But you mentioned earlier that the size of these sensors was a major problem in prior approaches. All this calibration doesn't help if the sensor is too big to fit, right? Now, how do we make the sensor itself smaller and more resource efficient without losing any of that critical sensitivity? This paper introduces another clever architectural change to achieve this: the dual clock TDC design.
Yes, the dual clock TDC.
How does a simple change to the clocking make such a big difference in physical footprint? It sounds almost too simple.
Well, sometimes the elegant solutions are simple in concept. What's truly fascinating here is how a subtle but powerful modification to the chip's internal clocking scheme for the TDC can dramatically shrink the physical footprint of each individual sensor. It's a really clever piece of engineering that solves a fundamental design challenge related to timing inside the TDC.
Okay, so what was the problem with the old way, the single clock TDC?
Let's first look at the limitations of the traditional single clock TDC design. In this setup, the same clock signal, let's just call it CLK, is used for two things. One, to propagate the electrical signal through our delay chain, our racetrack.
This signal being timed.
Right. And two, it's used to trigger the DFFs, our high-speed cameras, to capture the state of the delay chain outputs.
Same clock does both jobs. What's wrong with that?
The problem arises because of inherent asymmetric propagation delays of logic gates within the chip.
Asymmetric, meaning uneven.
Exactly. What this means is that due to tiny physical differences in the transistors, a low to high voltage transition, like the clock going from 0 to 1, might take slightly longer to propagate through a gate than a high to low transition, clock going from 1 to 0, or vice versa. This tiny asymmetry creates timing challenges inside the TDC.
Okay.
Because of this asymmetry, and to ensure accurate capture regardless of whether you're looking at a rising or falling edge, the sensor needs to wait almost an entire clock cycle for the signal to properly stabilize and for the capture clock edge to align reliably with the desired edge of the delayed signal propagating through the chain.
It has to wait a long time to be sure it gets a clean snapshot.
Essentially, yes. And this waiting period mandates a very long delay chain, lots of those delay buffer elements to be able to reach that optimal DC bias point we discussed earlier, the midpoint for measurement.
Because you need enough delay elements to stretch out the timing so you can find that sweet spot way down the chain.
Precisely. For the Intel Stratix 10 FPGA example they used, a traditional single-clock TDC might require an incredibly long delay chain, sometimes as long as 800 stages, 800 little delay elements.
800 stages. That sounds like a lot of gates.
It is. And of course, a long delay chain directly translates to a large sensor area on the chip, consuming precious silicon real estate and contributing directly to that large area problem this paper aims to solve. It's like needing an unnecessarily long racetrack just to ensure the camera can get a clear photo at the finish line, because the camera trigger is a bit slow or unpredictable.
Okay, so the single clock forces a long chain, which means a big sensor. How does dual clock fix it?
The dual clock solution, which is truly ingenious, elegantly bypasses this limitation. The core concept is simple but powerful. Instead of using the same clock for propagation and capture, this design uses a phase-shifted capture clock, let's call it CLK capture, specifically for triggering the DFFs, the cameras.
Phase-shifted, so it's offset in time relative to the main clock.
Exactly. In this particular research, they used a 180-degree phase-shifted version of the original CLK, basically an inverted copy of the main clock. And critically, as the paper notes, it shares the same clock distribution network, the clock tree, which helps avoid introducing extra timing uncertainty or noise into the system.
Okay, so an inverted clock for the cameras, how does that help?
How it works is quite clever. Imagine our race again. The main clock, CLK, starts the pulse down the delay chain track. The phase-shifted CLK capture is used only to tell the DFF cameras when to take their picture. By shifting this capture clock, its sampling edge, for example, its positive edge can be made to align much earlier and more reliably with the desired edge, say the positive edge, of the propagating signal, our delayed CLK, as it passes through the observation window.
Ah, so you don't have to wait almost a full cycle for things to line up? The shifted clock lets you capture it much sooner?
Precisely. It effectively shortens the time window needed for reliable capture. This allows the TDC to achieve that optimal DC bias point, the centered baseline, much sooner in the delay chain. It essentially shortens the racetrack needed significantly.
How much shorter?
For the Stratix 10 example, this architectural change reduces the required chain length from approximately 800 stages down to about 400 stages.
It literally halves it.
Roughly halves the length of the delay chain needed, yes.
Wow, and that directly saves area.
Absolutely. This has a truly significant impact on resource savings. This reduction in delay chain length directly translates to a substantial approximately 50% reduction in the TDC sensor size, specifically in the number of flip-flops and buffer elements required to build that chain.
Just by using a second shifted clock.
Just by using a second phase-shifted clock for capture. This is a crucial foundational step towards minimizing the sensor's area footprint, making it far more practical and affordable for integration into even the most resource-constrained designs. It means we can potentially embed these high-precision security assessment tools into chips that previously couldn't afford the silicon real estate.
Moving us much closer to that ideal of smart, proactive design being the norm.
Exactly, making powerful assessment feasible.
Okay, so we've explored the theory now from multiple angles. Strategic placement guided by the power delivery network, intelligent self-calibration of the observation window for perfect focus and PVT tolerance, and now a clever dual clock design for a significantly smaller footprint. This all sounds incredibly sophisticated and well-reasoned on paper.
It's a multi-pronged approach.
But the real test, of course, is in the real world. Does this intricate methodology, combining all these pieces, actually deliver on its promises when put into practice on a real chip? The paper provides compelling FPGA-based measurement results showing how all these pieces fit together to achieve, well, what sounds like a truly monumental impact.
Yes, and if we connect this to the bigger picture, these real-world experiments are precisely where the rubber meets the road. They're crucial. They not only rigorously validate the theoretical findings from the simulations, but also demonstrate a truly significant leap in efficiency for hardware security assessment.
Proof it works in reality.
Exactly. It's one thing to simulate a concept. It's another entirely to prove its effectiveness and impact on actual, tangible hardware.
So what was their setup for these experiments?
Let's delve into their FPGA-based measurement setup. They utilized an Intel Stratix 10GX FPGA as their test bed, a powerful, modern, and complex chip, so a realistic target. The device under test, the DUT, was a widely used open-source AES-128 cryptographic core. Using a standard algorithm like AES makes the results comparable and relevant.
Makes sense. And the sensors?
For their sensor deployment, they strategically placed 8 of their newly designed dual-clock TDCs across the FPGA fabric.
8 of them? Why 8 if 1 is enough?
Good question. They placed 8 in different locations to confirm the optimal placement strategy experimentally. If their theory about PDN boundaries and midpoints was correct, the sensor placed according to that theory should perform the best.
Okay. Testing the placement theory.
Precisely. And each of these 8 TDCs then had its observation window carefully calibrated using that ingenious greedy gradient search heuristic we discussed, ensuring each sensor was perfectly tuned for its specific location and the PVT conditions.
Okay, so 8 tuned sensors in different spots. How did they measure the leakage?
To assess the leakage, they used correlational power analysis, or CPA. CPA is a standard and highly effective statistical method for conducting side-channel attacks by correlating predicted power consumption for key guesses with the measured TDC output. This allowed them to determine the minimum traces to disclosure, the MTD, for each of the 8 TDCs.
Okay, finding the MTD for each of the 8 locations.
Right, and as we've learned, a lower MTD signifies higher leakage detected by that sensor and greater sensitivity to an attack. It tells you which sensor location is seeing the leakage most clearly.
So what were the results? Did one sensor stand out?
Now, for the measurement results, which are truly compelling and clearly shown in their figures, they show the variation in MTD across the 8 different TDC locations. And what stands out immediately is the striking superiority of TDC3.
But TDC3 was a winner.
By a significant margin. Among all 8 TDCs, TDC3 consistently required the least MTD, remarkably, under 150 traces to successfully extract the AES-128 secret key using CPA.
Under 150 traces, that's even better than the earlier example of under 200.
It is. It conclusively demonstrates that TDC3 was, without a doubt, the most sensitive location for detecting leakage across the entire fabric among the spots they tested. Its placement made it a beacon for those hidden vulnerabilities.
And where was TDC3 placed? Did it match their theory?
And importantly, yes. This result provided direct, real-world validation of their PDN theory. TDC3 was strategically placed exactly where their theory predicted the optimal spot should be, between the closest PDN boundary and the center of the DUT, the AES-128 core.
Right, at that midpoint.
Exactly. This perfectly confirmed the optimal placement strategy derived earlier from the sophisticated HSPIC simulations. The experimental results obtained from real hardware closely matched their theoretical predictions.
That's fantastic validation. Theory matches reality.
It's always a powerful indicator of robust and accurate research. It confirmed that their white box understanding of the PDN was not just a theoretical model, but an accurate predictor of physical reality on that specific FPGA.
Okay, so the placement theory works, the self-calibration works, the dual clock sensor is smaller. What's the overall impact when you put it all together?
And this brings us to the grand achievement, the headline result, really, of this combined methodology. By integrating these 3 powerful innovations, optimal placement guided by PDN understanding, the self-calibrating observation window, and the area-efficient dual-clock architecture, they achieved an approximately 8x reduction in sensor area.
8 times. An 8x reduction in the silicon area needed for this kind of assessment.
An 8-fold reduction compared to potentially needing multiple larger single-clock sensors spread across the chip to achieve similar coverage or sensitivity as suggested by prior work.
Okay, let's break that down. How do they get 8x? It's not just the 50% from the dual clock.
Right. It's not just the dual-clock design cutting a single sensor size by roughly half. It's a combination of factors. Optimal placement is key here. It means you don't need to spread dozens of TDCs across the chip hoping to catch the leakage somewhere.
Because you know exactly where to put maybe just one or a few.
Exactly. You might only need one, or perhaps a very select few, positioned in those precisely identified sweet spots. Combine that huge reduction in the number of sensors required with the dual clock's reduction in the size of each individual sensor, and that's how you get that powerful 8x overall area saving.
Fewer sensors needed, and each sensor is smaller. Multiplicative effect.
Precisely. Think about the practical impact. Instead of needing to dedicate a significant chunk of valuable silicon real estate just for security assessment infrastructure, designers can now integrate a highly effective assessment capability with minimal overhead.
Makes it much more likely they'll actually do it.
Absolutely. And there's another benefit. This reduction in the number of TDCs also dramatically lowers the memory requirements for storing all those delay values that need to be analyzed. Fewer sensors means less data to handle.
So the whole assessment framework becomes more efficient, less burdensome.
Far more efficient, yes, both in terms of hardware footprint and the subsequent data processing. It truly changes the game for practical, effective, pre-silicon security evaluation. It makes that concept of smart design a much more accessible and economical reality for a vast range of devices.
What an incredible journey, really, into the intricate world of hardware security. We started with securing cryptographic algorithms, which is, of course, incredibly important for everything from our phones to national infrastructure.
Fundamental.
Because those secrets are fundamental to our digital lives. But the beauty of fundamental research like this often lies in its wider applicability. This ingenious methodology for optimal TDC placement, self-calibration, area reduction, it surely extends far beyond just securing an AES-128 core on one specific FPGA, right?
Oh, absolutely. It feels like a foundational discovery for any kind of precise on-chip sensing where resources are constrained.
So this raises an important question for us. Where else can this advanced area-efficient voltage sensing technology make a significant difference? What are the broader applications?
That's a great question, and the answer is quite broad, reflecting the foundational nature of measuring minute voltage fluctuations with such precision and efficiency. The paper touches on a few key areas.
Okay.
First, consider fault injection, or FI, attack detection.
FI attacks, zapping the chip to make it glitch.
Essentially, yes. These are insidious physical attacks that often involve introducing momentary, controlled glitches, often large ones into the power supply or clock lines of a chip. The goal is to force it to misbehave, skip instructions, corrupt data, and potentially reveal secrets or bypass security mechanisms entirely.
Nasty stuff.
Very. TDCs, especially when optimally placed near sensitive logic and calibrated using these techniques, can be utilized to detect these large supply glitches, which are often characteristic fingerprints of fault injection attacks.
So the TDC acts like a glitch detector.
It can, yes. It provides a crucial on-chip defense mechanism, allowing the chip itself to sense when it's under physical attack, perhaps log the event, or even take countermeasures like resetting or halting.
Built-in physical security alarm. Cool. What else?
Beyond active security threats, this technology is invaluable for general operating condition monitoring.
Monitoring the chip's health.
Exactly. Imagine a chip that can effectively take its own pulse and monitor its own health in real time. This includes tracking critical parameters like aging.
Aging? Like chips get old and tired?
In a sense, yes. Component performance subtly degrades over the lifespan of a chip due to physical effects like electromigration or transistor wear out. This degradation, or aging, can lead to reliability issues or timing failures down the line. Precisely measuring voltage and timing shifts with TDCs can help monitor this aging process.
So you could predict failures?
Potentially enable predictive maintenance, yes. It can also precisely monitor thermal variations or temperature changes across different parts of the chip. Temperature directly impacts performance, power consumption, and longevity. Mapping these variations is important.
Like a thermal map.
Furthermore, it provides general load monitoring through the detection of those high-frequency voltage overshoots and droops we discussed. It essentially acts as a real-time traffic monitor for the chip's power demands across different sections.
Understanding how hard different parts are working.
Exactly. This kind of self-awareness, enabled by precise, low-overhead sensing, can enable dynamic performance tuning, better power management, and ultimately more reliable and longer-lasting devices.
So security, reliability, performance. It's quite versatile.
It is. And finally, the beauty of this methodology is its generic nature. It's not fundamentally tied to a specific type of cryptographic algorithm or even just security applications. It can be applied to a whole host of emerging security-sensitive applications.
Like what?
For example, the paper mentions it's highly relevant for assessing the security of machine learning accelerators on remote FPGAs.
Ah, AI hardware. That's huge right now.
Absolutely. With the explosion of artificial intelligence and machine learning, these specialized accelerators are becoming critical components in everything from massive data centers to tiny edge devices in your phone or car. And guess what?
They leak information too.
Power side channel vulnerabilities are already a known concern for them. Their complex computations also leak distinct power signatures that could potentially reveal information about the AI model itself or the data it's processing.
Stealing the AI model or the input data through power analysis.
Huh.
Wow.
It's a serious concern. This research provides a powerful, efficient, and proactive tool to assess and hopefully mitigate those vulnerabilities in these new, complex, and increasingly vital systems, ensuring the integrity and confidentiality of the AI models and the data they process. It's a tool that grows with the technology it needs to protect.
What an incredible deep dive that was. We've really journeyed into the intricate world of hardware security, haven't we?
We certainly have, down to the physics.
We've seen how understanding the invisible physics of a chip's power delivery network, something most of us never think about,
Definitely not.
combined with clever circuit design like the dual clock TDC and intelligent placement strategies based on that PDN knowledge, can truly revolutionize how we protect our digital infrastructure.
It's a paradigm shift from just hoping it's secure.
And this isn't just about making things incrementally more secure, is it? It's about making security assessment dramatically more efficient, more accessible, and profoundly more accurate during those critical design and pre-manufacturing phases.
Getting it right early.
It really feels like the essence of building security in from the ground up, rather than trying to bolt it on later as an afterthought.
That's the goal. And it truly highlights that even in the most complex, high-tech systems operating at a microscopic level, sometimes the simplest, most fundamental insights, like precisely where you place a tiny sensor or how you optimize its internal clocking, can yield the most profound impact.
The fundamentals matter.
Always. This research shows us a path to working smarter, not just harder, in the ongoing, vital effort to find and mitigate critical vulnerabilities hidden deep within our hardware. It ensures we're not just throwing resources blindly at a problem, but directing them with surgical precision based on understanding the underlying system.
Working smarter, not harder. A great takeaway. So maybe a final thought for our listeners to chew on.
Okay. Well, as our digital world becomes ever more reliant on complex, integrated hardware for literally everything,
Everything.
how might this principle of optimal placement, this idea of deeply understanding the physical system to find the most effective points for observation or interaction, extend beyond just security sensors?
Interesting.
How could a deep understanding of physical systems, whether it's power delivery or heat dissipation or signal propagation, and the strategic positioning of measurement or control points based on that understanding, how could that lead to breakthroughs in other areas of system design? Areas where efficiency, precision, and maybe avoiding overwhelming information overload are paramount. What else could we optimize beyond security by truly understanding its underlying physical landscape first?